Today we're going to look at section 4.5, which is called exponential growth and decay and modeling data. So today we're going to model exponential growth and decay, and we're going to model data with exponential and logarithmic functions. So exponential growth and decay. One of algebra's many applications is to predict the behavior of variables. This can be done with exponential growth and decay models. Okay, so we've already kind of talked about exponential growth and decay when we graphed exponential functions at the very beginning of this chapter, but we're going to look at it a little bit more. Okay, so noticing the pictures off to the right, these are exponential graphs. Like I said, something that we've already been doing since the beginning of this chapter. But the mathematical model for exponential growth or decay is given by this. A equals A sub O times e to the kt power. Okay, so the base is going to be e. And what's going to help us determine if we are growing or decaying deals with the k value. Okay, if k is greater than 0, so a positive number, then the model is going to be growing. So it starts small, gets bigger as it's heading towards the right. However, if k is less than 0, so a negative value, that's when the model is going to decay. So it starts big and it's getting smaller as we move to the right. So in 1990, the population of Africa was 643 million, and by 2000, it had grown to 813 million. So we're going to use that model, A equals A sub O times e to the kt power, in which t is the number of years after 1990, and we're going to find the growth function that models the data. Okay, so essentially the growth model is going to be taking that A equals A sub O times e to the kt power. We're going to want to substitute in something for A sub O. We're going to want to find k, so we can plug that in as well, and then that would be our model. All right, so notice that the numbers that they're giving us, it starts with 643 million in 1990. It ends with 813 million in 2000. So that 18, or why do I keep saying 18? 813 is going to be the A, while the A sub O is going to be that 643. Okay, so we'll start with 813 to equal 643. Our base is still E. Notice that we don't know what K is because we don't know what the growth rate is. However, we do know what T is. Because we're starting in 1990 and we're ending in 2000, well, what's the difference between those? Well, that's a 10-year difference. So T is going to be 10. All right, so in order to start solving for K, which is an exponent, I got to isolate the base by itself. So I'm going to divide both sides by 643. I'm going to keep that fraction as it is so I can get to the most exact answer. We'll now have e to the 10 times k power. And now that I've isolated that base by itself, remember, in order to get rid of the base, I'm going to take the natural log of both sides. So taking the natural log of 813 divided by 643, that's going to equal, now when I take the natural log of e raised to that 10k power, the e and the natural log cancel, so it's really then just going to equal 10k. So then I'm going to divide both sides by 10, and that's going to get me my value for k. All right, so once again, make sure that you are very carefully typing this into your calculator. So we're going to do the natural log. We'll do 813 divided by 643, close the parenthesis, and then divide by 10. And let's do this. Let's round to 3 decimal places. So if I look at my decimal, it's going to be 0. So then notice how it says 0, 2, 3, 4, 5, 8, 6, 3, 9. So 3 decimal places, 0, 2, 3, because the 4 is going to keep the 3. Okay, so now we found our k value. We can substitute it in now to find the actual model. So remember, the model is going to be that A equals, we will keep our original number here for A sub O, so 643, technically million, and then we'll have E to the 0.023 T power. Okay, so that means then I can tell you any amount of time after 1990, we can plug it into that model and we would know the population of Africa. So there's my model. Okay, so now that I have that model, I want to use that, and it says, by which year will Africa's population reach 2,000 million, which is technically 2 billion. Okay, but I want to keep everything in terms of the millions so we can easily do this. Okay, so now I don't know what T is, but I'm going to use the model that we just came up with. I know that now if this is 2,000 million, I want that to be my A value. So we're going to have the 2,000 equals 643 times E. We know what our K is. It's 0.023. And now I don't know what T is. Okay, so once again, to get us started, I have to isolate that base by itself. So I'm going to divide both sides by 643. I'm going to just keep that fraction as it is. So 2,000 divided by 643 is now going to equal E to this 0.023 T power. Okay, so now I want to get rid of the base. So I'm going to take the natural log of both sides. So we'll have the natural log of 2,000 divided by 643. Remember, when I take the natural log of E, those are inverses, they cancel, so it will just leave us with the exponent, which was that 0.023t. And now I'm going to divide both sides by that decimal so I can get t by itself. All right, so carefully type this into your calculator. So natural log 2,000 divided by 643, close the parentheses, then divide by the 0.023. Okay, we do have a decimal. It's 49.33729284. So that means that our time is going to be approximately 49 years. Okay, so because it's approximately 49 years and it says by which year, because my model starts in 1990, I'm going to take 1990, I'm going to add 49 years onto it. And so that's going to tell me that we reached that 2 billion mark in 2039. Okay. All right, so here's my next one. It says in 2000, the population of the Palestinians in the West Bank, Gaza Strip, and East Jerusalem were approximately 3.2 million. And by 2050, it's projected to grow to 12 million. So once again, we're going to use that A equals A sub O times E to the KT power, in which T is the number of years after 2000, to find the growth function that models the data. So once again, because I know that we are going to start with approximately 3.2 million, that's going to be your A sub O. We're ending with 12 million, so that is my A value. We know that T is the number of years after 2000. So because we're projected by the year 2050, I know that I want T to be 50. So that's everything that I need in order to then find K. So we'll have 12 equals 3.2 times E to the K times 50. All right, so I got to isolate that base. I'm going to divide both sides by 3.2. Once again, I'm going to leave that as a fraction. I'm going to take the natural log of both sides. So the natural log of 12 divided by 3.2. When I took the natural log of E, that really then just leaves me with the exponent, which is 50k. I'm going to divide both sides by 50. I'm going to very carefully type this into my calculator, and I want to surround to 3 decimal places. So hopefully by you typing that into your calculator, we see that we should get 0.026. Okay, so that's my K value. So then what's the model? Well, it's going to be that A equals, we'll start with the 3.2 million, and it's E raised to the 0.026 T power. There is my model. All right, so then moving on to part B of this. So we're going to use the model that we just came up with, but now it says, in which year will the Palestinians' population be 9 million? Okay, so now I want this to be my A value. We already have our K. We have our original A sub O is 3.2. Okay, so we're going to have 9 equals 3.2 times e to that 0.026 t power. So let's figure this out. Notice that because in the original problem, we got it to be 12 million, and here I only want it to be 9. Hopefully you are noticing that we should end up with a year that's less than 2050. Okay, so just keep that in mind as we go through this. So we're going to isolate that base by itself. So I'm going to divide both sides by 3.2. Once again, then I want to take the natural log of both sides. So we'll have the natural log of 9 divided by 3.2. When I take the natural log of the other side, the natural log and the e cancel. And so that leaves you with the exponent, which was the 0.026t. And then to get that t by itself, I'm going to divide both sides by the 0.026. Okay, so that's going to be approximately 39.7. So I'm going to round it up to the nearest year. So that's approximately then 40 years. Okay, so once again, because this was talking about starting the population in 2000, and now we're talking about 40 years later, well, 2000 plus 40 tells us that the year the population is at 9 million would be 2040. All right, let's talk about half-life. Some exponential decay models are used when determining age of fossils or artifacts. This method is based on considering the percentage of carbon-14 remaining in the fossil or the artifact. Carbon-14 decays exponentially with a half-life of approximately 5,715 years. Okay. So we're going to use that fact that we have 5,715 years with that carbon-14. So that's going to be used to decay to half the original amount to find the exponential decay. Okay, so remember, our model for growth and decay is that A equals A sub O times e to the kt power. Okay, so that's my model. I'm talking about having a half-life, which means I don't really need to know what A and A sub O is, because when I go through the process of starting to get that base of E by itself, remember, I'd have to divide both sides by A sub O. And if we're talking about half-life, that means that when I divide both sides by this A sub O, this division right here is going to turn into a half. Okay, so that's what it's talking about when we're talking about a half-life. So that's still going to equal e raised to the kt power. But now we're talking about t representing 5,715 years. So that's what I'm going to plug in for t. Okay, and then this is going to allow me to solve for k. So remember, because we're now talking decay, all of our other problems, our k value was a positive number. Granted, it was a very small positive number, but positive because we were growing. Here, because we're talking about decaying, we should end up with a k value that is negative. So if you don't end up with a negative, you know that you made a mistake somewhere. All right, but I'm going to take the natural log of both sides. And remember, when I take the natural log of e, it's just going to leave me with that exponent. And then I'm going to divide both sides by that 5,715. And that's going to get me a k value. Now, this is going to be pretty small, but notice how when you divide, you should get a negative. So we're going to get negative 0.000121. Okay, so super, super small, but notice that it's negative because we are decaying. Okay, so it wants us to find the exponential decay model. So my model is going to be that A equals A sub O times e to this negative 0.0000121 t power. All right. All right, so now it says that in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found. Analysis indicated that the scroll wrapping contained 76% of their original carbon-14. We're going to estimate the age of the Dead Sea Scrolls. Okay, so in the past, when we did this last example here with the half-life, we ended up dividing and we got a half, which remember, 1/2 is technically 0.5, so that's like 50%. So they lost 50% when they were decaying. Okay, so that's why here, when it's talking about how we have now 76%, that means that when we divide our A and our A sub O, we have 76% left, which is then going to be 0.76. That's going to equal E raised to that K value that we just got, so that negative 0.000121. And we're talking about how we don't know the amount of time. So I don't know what T is. That's what we're going to find first. Okay, so hopefully that model makes sense. Okay, so the K value we just got from the other part A. All right, we divided to have 76% left, but that is written as a decimal there. All right, so now I want to start solving for T. So I'm going to take the natural log of both sides. And remember, when I take the natural log of E, it's just going to leave me with that exponent. And so to get T, we are going to divide both sides by that negative 0.000121. So we will then approximately get 2,268. Okay. So this is the amount of time that is happening since 1947. Okay. So then notice that we are technically now in the year 2021. Okay, so thinking about what's the amount of time that's passed since 1947? Well, that's been what, 74 years? Okay, so the amount of time that we got for T, that was the model dealing with 1947. Now we're 74 years past that time. So we are going to take this 2,268, we'll add 74 onto it, and that's going to tell us that we are what? That these scrolls are 2,342 years old. Okay, so that's us modeling with exponential growth and decay, and we can model with exponential and logarithmic functions.